Hello everyone. In this video we're going to cover chapter A. The chapter A is just a probability review. If you took Math 380 or a similar class, you should have seen most, if not all, the concepts we're going to cover right now. And then at the end you will see the connection to what we're doing in Math Finance. So we're going to have a probability space. The probability space will consist of three parts: the sample space, an algebra, which may be a new concept, and a probability. Okay, in this case, P stands for the market probability, which we talk about it, and that doesn't give you the fair price, but it's still the market probability. So omega is the sample space. Remember, the sample space is the set of all possible outcomes or all possible simple points. So for example, let's say that a family decides to have three kids. So the sample space will be the following. The first one could be a boy or a girl, and then the second one could be a boy or a girl, boy and a girl, and so forth. Okay. So in this case, the sample should be 3, 3, 3, 3. So the sample space will be the following. You can have 3 boys. You can have a boy, then a boy, then a girl, and so forth. So the last one will be 3 girls. So in this case, you have A outcomes. Then once you have a sample space, you can have events. For example, E could be the event of having 2 girls and 1 boy. So the probability of E will be 3 eighths. You can see from here. So this is 2 girls and a boy. This is 2 girls also and a boy. And this is also 2 girls and a boy. So that's 3 out of A. Also remember, for every event, you have the complement. So for any event A, you have the complement. So remember, A is the complement of A, and A union the complement is equals to the sample space. So it is means crazy. So the opposite of crazy is not crazy. So all people are either crazy or not crazy. So that will give you the whole sample space. The next part of the sample space is an algebra, and this may be something that you may have not seen before. Okay. So what is an algebra? So an algebra is a collection, okay, of subsets of omega such that the following is true. Number 1, the omega or the whole sample space belongs to the algebra. And number 2, that if A belongs to the algebra and B belongs also to the algebra, then the following must be true. Part A, that the union also belongs to the algebra. B, the intersection also has to belong to the algebra. And then A minus B, which technically means A but not B, also belongs to the algebra. Remember, the A not B means the following. you have a sample space omega, and this part is the intersection, so this is A and B. So this part in blue means it's part of A, but it's not part of B. This will be A and this will be B. Right, so here are some classic examples of algebras. So the most basic one is the trivial linear algebra, which will have the whole sample space and the empty set. So here clearly, well, you can see that the first part is satisfied, and then if we do the union, so everything union with the empty set is equals to everything, which clearly belongs to the algebra. So this checks, so part A checks. Then part B, if we do the union, so the intersection of everything with nothing, you get the empty set, which also belongs to the. And obviously, if we do omega intersect with the complement of the empty set, so this is just omega again, which clearly again belongs to the algebra. So there is a reason why this is called the trivial algebra, okay? Because you're just using everything and nothing. All right, another example with the following. This is equals to A for some set A. You also have the complement omega in the empty set. All right, so make sure you don't confuse A with the algebra. So this is the algebra and this is a set called A. Okay. Now this is probably one of the most important algebra we'll use, and this is usually called the algebra generated by the set A. So generated by A. So let's check the conditions. So on this one, well, clearly condition 1, omega belongs to A, so this is good. And for 2, notice the A union a complement is equals to omega, which again belongs to A. So it will be part A. And then part B, A intersecting the complement will give you the empty set, which again belongs to A. And then finally you can check that part C also belongs to A. Just check this, should be obvious. And the last example of algebra we're gonna deal with is the following. So the algebra will be the set of A such that A is a subset of omega. So this is the algebra of all subsets of omega, including the empty set. Okay. So these are the three algebras we will be dealing, mostly this one. But now you have an idea of what a algebra is. I don't think in Math 380 they talk about algebra, so this is just a more formal way to look at probability. And obviously you have a probability measure, which remember this was the market probability, where the probability omega has to be obviously be 1. The probability of the empty set is 0. And then the probability of any set has to be between 0 and 1. Okay. Now the next thing that you cover in probability is independence. So remember that two events, A and B, independent if the following is true. The probability of A and B is equal to the probability of A times the probability of B. In general, if you have more than two, it's the same idea. So in general, the probability of A1 intersecting with A2 intersecting with A3 and so forth all the way to AK is equal to just the product of the probabilities of AI from I equals to 1 to K. And the last thing related to independence is called conditional probability. So this is also going to be very useful. So conditional probability, which says the following: the probability that A is going to happen given that B already happened is equal to the probability of A and B divided by the probability of B. Now notice that if A and B are independent, A and B are independent, then the probability of A given B is just equal to the probability of A, or the probability of B given A is just equal to the probability of B. The next topic we need to consider or review is the concept of a random variable. Remember that a random variable can be either discrete or it can be continuous. There are several definitions of random variables, so we're gonna go with the following for this class. So a real value random variable, which will be denoted by Kc, which depends on omega, is a real value function on the sample space that is A, measurable. So this may be a new thing that you may have never seen before. So I will explain what that means. A measurable means the following: any set of this form, which means that for all the omega that are part of the sample space, such that the random variable evaluated at the value omega is less than or equals to some x, that this set belongs to the algebra. So that's what it means. Now, for the point of view of math finance or mathematical finance, what this means is that you can only use information up to now, which should be obvious, but that's what it means. If you want to calculate the price of something, you can only use past information until the up to current information. In other words, it means that you can not look into the future, which would be nice, but you cannot. Okay, so that's what measurable is going to mean for the purpose of our class. Now, indicator functions are going to be very useful too. There are several ways to denote indicator functions, but the book uses the following. The indicator function for a set A, you can also write it like this, because it's going to depend on the value omega, and this is equals to 1 if omega belongs to the set A, or 0 if omega doesn't. Okay, so therefore, if you let Kc omega be a random variable defined on the set x equals to x1 all the way to xk, and then you let AI to be the set of omega belonging to the sample space such that Kc of omega is equals to xi, then that implies the Kc omega, which will be the sum from I equals to 1 to k of xi times the indicator function. So this will be a discrete random variable. Okay. We also want to talk about continuous random variables later on the second part of actually the last part of the class. Now let's look to the properties of expected values. So by definition, the expected value, assuming that you use the probability P. Remember that P was the market probability. So this is going to be very, very important that you are aware which probability we're using. So with respect to P, this is a definition of expected value. Expected value of a random variable is equals to the value of the random variable times the probability that will happen from 1 to m, or depends how many you have. Okay. So now here, if we assume that the expected value for Kc is finite, and the expected value for nu is also finite, we have the following three results that you need to remember over and over. The first one is obvious. The expected value of a constant is just equals to the constant. Now, if you multiply the two random variables Kc and nu by constants, then the expected value of the sum should be equals to the sum of the expected values. And this is just the property of linearity. Now the third property should be obvious too. If Kc is less than or equals to nu, then the expected value of Kc should be less than or equals to the expected value of nu. Now remember from the past what we did in the previous lectures. Remember we have the model where the stock price is 0 right now, and tomorrow it can go up, and or tomorrow or whenever is the day it can go down. Now the book uses the following notation, which is not the best, but that's what the book uses. So it will call this 1s1 and this is 2s1. This just means the first value if it goes up and the second value if it goes down. And remember we used the probabilities that this was 1 minus p, that it will go up, and p that it will go down. And then if you find the expected value, which we did, of the payoff function, remember this was equals to p times f of a plus 1 minus p times f of v. But remember that this was not deferred price. Okay, so we'll talk about that a few times before. And not only that, this is emphasizing now that we're taking expected value with respect to this probability. So recall that the deferred price, which you have this on the test, okay? The first price was given by B0 or C0, which was equals to phi S0 plus psi, which we have the following formulas to find this. Again, this is what you just have in the test. And if you rearrange things slightly, you can write the whole thing into a single formula like this, was equals to e to the minus r delta t f of v, and then e to the r delta t minus 1 plus a divided by v minus a plus f of a times 1 plus b minus e to the r delta t over v minus a. Then if you pay close attention to this is what we call a q, and q, well, it will be defined as e to the r delta t minus 1 plus a over v minus a. And we already show that q is a probability. In fact, it's between 0, 1. And you can check, you should check that this is exactly 1 minus q. So therefore, this is exactly the same thing as e to the minus r delta t times f of v times q plus f of a times 1 minus q, which is technically the definition of another expected value. So this will be equals to e to the minus r delta t times expected value, but now with respect to q instead of p of the payoff function. And remember, this is the actual price. In fact, this is the arbitrage free price, or the no arbitrage price. So therefore q now, which will be the new probability, has several names, but q is called the risk neutral probability. That's one name. Is also called the risk free probability, and is also called the implied probability. Okay. So to recap, because this is very important, because this relates to what we'll be doing the whole class, if you do the expected value with respect to p, which was the law of large numbers, that will not give you the default price. But if you do the expected value with respect to the risk free probability, and you discount it, that gives you exactly the fair price, meaning the arbitrage free price or the no arbitrage price. The next thing to review from probability is the joint probability distributions. So remember, if you have the joint probability distribution of Cassie and Nu in the discrete case, this is defined to be the probability that Cassie is equals to x and Nu is equals to y, where x belongs to capital X and y belongs to capital Y. Now, if they are independent, then that implies that the joint probability of Cassie and Nu is just equals to the product of the probabilities. So that's the best thing that can happen. Where, remember, this means the following. This is the probability of the set omega such that Cassie is equals to x. Now, if x and y are independent, that also gives us something very useful. Expected value with respect to p of Cassie and Nu is just equals to the product of the expected values. Okay, which also makes finding expected values if they are independent. Now, the last concept that we're going to be using a lot is the idea of conditional expectations. So by definition, the expected value with respect to P of K given that nu is equals to some value y is defined to be the sum from j equals to 1 to m of xj times the joint distribution of the joint distribution of K and nu divided by the probability of nu, okay? And this is technically just the sum from j equals to 1 to m of xj times the probability that K will be equals to xj given that nu is equals to y. Here xi belongs to x and y belongs to y. So here, to be more specific, this means the conditional expectation of K with respect to nu equals to y. The following properties are going to be very, very useful. So the first one is the nested expectations. Okay. So what that means is that the expected value of K, this is not a conditional expected value, is equals to the expected value of the conditional expected value. This property is going to be used multiple times. The second one says the following, that if K is independent of nu, then the expected value of K, given that nu should be just equal to the expected value of K, which makes sense. Number 3 has to do with the measurable stuff that I talked at the beginning. So what this is saying, the expected value of K times nu, given that K, so you know the information up to this point, so therefore you can just take this out because you know what this value is. So therefore this will be equals to K times the conditional expectation of nu given K. And number 4 was kind of obvious. The expected value of K, given that K, should just be K. Now I already say this a couple times, but let me tell you one more time. We're going to use these properties a lot, especially the last part of the class. So make sure you become very familiar with them, or if something doesn't make sense, just ask me during the office hours or during the class. But these properties are going to be very, very useful. Now, up to this point, we have done only one step. So we're going to start looking into two steps. This is going to be by one step. This is what you have on the test. If you start with 0, then remember it can go to 1 as 1 or 2 as 1. And this probability was 1 minus p, and this was p. This is time equals to 0, and this is what we call a binary tree, and it was only one step. Right, so now let's consider now 2 steps. So now this will be 1 as 2. This will be a 2 as 2. And then here you're going to have 3 as 2. Now it's very important to notice that these two are exactly the same. And then 4 as 2. Remember, this is the 4 value for the second second step. Remember that this means that S1 can go here or can go here, and S2 can be here, here, or here. So recall that S1 is essentially S0 times 1 plus Kc. Well, remember Kc has two values, and I will give you this one or this one if it goes up or if it goes down. So let's say that I ask you to find the conditional expected value with respect to P of S2 given that S1 is equals to 1S1, which means you end up here. So then that should be equals to 1 minus P times 1S2, which is this value right here. Remember the probabilities here remain the same. It should be 1 minus P. This is P, 1 minus P, and this is P. Plus P times 2S2. So this is saying what's the probability, what is the expected value of getting to S2 given that S1 is equals to 1. So given that you went to here, well, the two choices are this or this, which is this one and this one. Also notice, so this should be obvious, but if it's not, the 1S2, which is this point right here, to get there, that means you have 1S1, which was this value, and you have to multiply times 1 plus b to go up. And therefore 2S2 will be equals to this value, but now you went down. So this should be 1 plus a. Hence, we will get the following. This is 1 minus p times 1s2, which is this value right here. So that will be 1s1 times 1 plus b, and then plus p times 2s2, which is equals to 1s1 times 1 plus a. And then you can factor the 1s1, which again is, that means whatever is the value here. And then this will be 1 plus b plus p a minus b. So make sure you check the algebra. Now if we do the same thing, but assuming that now we went down instead of going up, and the process is identical, you just have to switch the values. So now we're assuming that S1 went down. So if that's the case, then this will be now 1 minus p times 3s2, which will be this value, plus p times 4s2. And again, once you simplify the whole thing, and you should definitely check this, you will get 2 is 1 times 1 plus b times p times a minus b. Alright, so don't forget that we're using the following. S1 is equals to S0 times 1 plus Kc1, which we did already. And therefore S2 will be now S1 times 1 plus Kc2. Alright, so therefore now we can find the following, which it looks the same, but you have to be very careful that this is very different than the previous two. What is the expected value of S2 given S1? Well, then by definition, this will be the expected value with respect to P of S1 times 1 plus Kc2 given S1. That's the definition. Now the main difference between here and these two is that here we have the whole S1. Well, here we're being very specific. What happens if it goes down, and this what happens if it goes up. and this is saying what will happen if it goes up and down. Essentially, that's what it means. Okay, so now here we have notice that you have S1 here and S1 here. Also notice that S2 is equals to this. So therefore, by property number 3 that we just have in the previous page, since this is measurable with respect to this one, so you can just take it out, so it will be S1 times the expected value of P of 1 plus C2, okay, given S1. Then by property number 2, this is equals to S1, the expected value with respect to P of 1 plus C2 only. Why? Because this is independent of S1. Alright, so from here we will have that this is equals to S1 times 1, because the expected value of 1 is 1, since 1 is a constant, and then plus S1 times the expected value of C2. So therefore this will be equals to S1 plus S1 times the expected value of C2 is going to be 1 minus P times B if it goes up, plus P times A if it goes down. The exact same thing we did before. So then you can factor S1. It will give you 1 plus 1 minus P times B plus PA. And then if you rearrange the inside, this will give you 1 plus B and then plus P times A minus B. Okay, so now notice the similarity between this and if you add these two answers. Okay, so that's the difference between finding the conditional expectation given a specific value, then finding the conditional expectation of a variable given another full variable. So next time we will find the price in more than one step with actual numbers. So this is just the reasoning behind why the theory works and why it's mathematically true or mathematically sound. Okay, so that's it.